Recall that in Chapter 2, we learned all about limits, and we learned different techniques for finding limits. The first one that we would always try was direct substitution, and if that led us to something that was not defined, then we had other things we could try. Now, in Section 4.5, we're going to learn another technique called L'Hopital's rule that will allow us to evaluate limits that have these certain, as they're called, indeterminate forms of 0 over 0, or infinity over infinity, or 0 times infinity, or infinity minus infinity. Okay, so what the rule actually says, again, it's called L'Hopital's rule. It looks like L'Hospital's rule, but the S is not pronounced, and this is a French name, so L'Hopital is how we say it. So we have these functions f and g that are differentiable. G prime cannot be 0 near a, so a is the x value that's being approached in the limit. And either f and g limit as x approaches a are both 0, which means the indeterminate form we have is 0 over 0, or the limit of f and g as x approaches a is infinite, plus or minus infinity, which means we have the indeterminate form infinity over infinity. Then L'Hopital's rule says that if we want the limit of the ratio f over g as x approaches a, we can get that by taking the limit of f prime over g prime, the ratio of derivatives, as x approaches a. And one thing I want you to notice here is that we are not, in fact, using the quotient rule. This is something that sometimes students get confused about because we've just spent all this time learning these shortcut rules for derivatives. And when we see a ratio or a quotient and we're thinking about derivatives, then we might naturally want to use the quotient rule. But this is actually inside of a limit. The ratio of f over g is inside of a limit. So when we get those particular indeterminate forms, 0 over 0 or infinity over infinity, the rule says that instead of taking the limit of f over g as x approaches a, we can take the limit of f prime over g prime as x approaches a, and there's no quotient rule at all. Now, note to self, it says here, if the limit on the right side exists or is infinity or negative infinity. So just a reminder, one of the things that we learned in Chapter 2 is that we can use the notation that a limit equals infinity, but we have to understand that an infinite limit is a limit that we actually would say does not exist. But when we write equals infinity, it's just a way for us and our audience to know that those output values are increasing without bound. Okay, so your book gives you a couple graphs to try to understand why L'Hopital's rule makes sense. Now, this is not a proof at all. It's just sort of a visual to kind of help you see where things are coming from. So we have these two functions, f and g, and their limits as x approaches a are both 0. And in fact, let's just remember what we learned in section 3.9, that we can use the linearization to approximate function values. So what your book is saying is that if we were to zoom in on these curves f and g, of course they would look like straight lines. And if they were actually lines, then the pink function would be m1 times x minus a, and the blue function would be m2 times x minus a. So let's just take a moment to see why that works. Okay, using the idea of linearization. So f of a and g of a are both 0, right? We can see that in the left-hand picture. And the linearization says that f of x is approximately f of a plus f prime of a times x minus a, and g of x is approximated by g of a plus g prime of a times x minus a, and those approximations will be good when x is near a, which is important because we're in the limit, we're letting x approach a. But the thing is, since the f of a and the g of a are both 0, those two equations then, if we replace the f of a and the g of a with zeros, what we're really left with is that f of x is approximately f prime of a times x minus a, and that g of x can be approximated by g prime of a times x minus a. Again, if x is near a, which it is if we're letting x approach a in our limit. So what your book has shown here is that we can replace f with m1 times x minus a and g with m2 times x minus a, and of course the x minus a's cancel, but this slope m1 is really f prime of a, and the slope m2 is really g prime of a. So when we take the limit of the ratio, thinking about the idea of linearization, what we really wind up with is a ratio of slopes, and those slopes are given by derivatives. Now notice that in this limit statement, which again is L'Hopital's rule, assuming the conditions have been met, instead of writing that the limit of f over g as x approaches a is f prime of a over g prime of a, we have that it's equivalent to the limit of f prime over g prime as x approaches a. Now, what that's going to allow us to do is use L'Hopital's rule more than once if we need to. The fact is that in this limit on the right-hand side of f prime over g prime as x approaches a, our first option will be direct substitution, which would give us f prime of a over g prime of a. And if that limit exists, then great, we can use it. But sometimes we might get the indeterminate form a second time and have to do L'Hopital's rule a second time, or even a third time, as you'll see in some of the examples in your book.